All right, so welcome back from our brief break. So this will be the, or rather short, final installment of our 17th lecture. And in this case, we're going to be talking about what the effect of energy dissipation. Energy dissipation. So what we learned in the first half of this course, the first half of this lecture, is that spin about intermediate axis is inherently unstable. That's always the case, and it will continue to be for this lecture. But we did make this conclusion that spin about the major axis or the minor axis are both neutrally stable, so stable. Right? But we neglected a great deal of internal dynamics, a lot of equations of motion which didn't sort of fit into that narrative. So we just used a linearization of Euler's equations. But real spacecraft have more going on than just playing cards or books or tennis rackets do. Tennis rackets, by the way, are also a favorite of YouTube videos of intermediate axis theorem. Right. So in particular, if we look at this this spacecraft, what is this spacecraft? This is Explorer 1, I think. Maybe Explorer 2. It says on the next slide. Explorer 1. Right. This was our first satellite that the U.S. launched. Remember, the Russians launched Sputnik. They also had some problems with Sputnik, but we're not going to talk about them. And basically, it's a rocket. They launched a rocket into space. Hey, we have some ICBM, so we launch one into space and say we have a satellite. Right? So they did that. And it never separated. We never had separation of our booster stages. Right? These things were still attached. Right? Fuel tanks. We dropped out some wires for antennae. Right? These are the antennae. Right. And so we launched it into space, and we tried spin stabilizing it. So we spun it about its axis, minor axis, obviously, as you can see from the geometry here. That makes, of course, in our analysis, this the z-axis. Unfortunately, what happened with Explorer 1 was that it almost immediately started tumbling. Right? So it was initially spun up around the z-axis right over here. And we saw that the angular velocity vector migrated fairly quickly from an angular velocity vector here to a final angular velocity vector about this, I don't know, let's call it omega x. Right. And this was unpredicted, right? This was, we didn't realize what this was going to happen, obviously, or we would have designed it differently. And so it prompted a lot of research into why this was happening and how to avoid it. Right? And so this is, we started using Euler's equations more seriously. Of course, Euler, right, was from the 1800s. Early 1800s, and his equations had been around for a while, but we started looking into how those equations could be used to predict this effect and how to neutralize them. So basically, so again, what's going on, right? So what's going on is that there's internal dynamics. So there's internal motion of these antennae, for example. There's internal motion of fuel. So it has little waves, it splashes against the sides of the tank, the leftover fuel, and of course there's the sun over here, right? There's the sun. The sun's not very bright, which is heating the spacecraft and causing a structural expansion and contraction, and energy is being absorbed and energy is being dissipated, and basically all of these effects, right, result in dissipation of energy ultimately. So we knew that if you spun something about if you spun something up, the angular momentum vector wouldn't change, right? The angular momentum vector is fixed, right? H is fixed. However, what it didn't take into account was that kinetic energy, or energy in general, is not fixed. Kinetic energy is what we'll focus on. So kinetic energy, typically in these cases, is dissipated. Right? It turns into heat energy or some other form of energy and goes off into space. Right? And so how does that affect the motion? Obviously, we can't model the fuel sloshing. That would be too complicated. So we're going to make some approximations or some simplifications and try and study how changes in kinetic energy affect stability of rotation. Anything I missed here? Started precessing and then decayed to a flat spin. This was our first try. We eventually got better at designing spacecraft. We no longer design spacecraft which have this prolate structure, right? So if you see modern spacecraft, they tend to be fat. They tend to have the oblate. And why are all our spacecraft look oblate, where all our missiles look prolate? Well, in the atmosphere, we can dissipate these disturbances into the atmosphere, but we can't do that in space. And so that's the problem. So let's look at an analysis. So first of all, if we're talking about dissipation of kinetic energy, it's worth talking about the definition of kinetic energy, right? So kinetic energy, as you may have learned, is like 1/2 mv squared. Well, that's translational kinetic energy. We're not interested in translational kinetic energy. We're interested in rotational kinetic energy. So what is rotational kinetic energy? So that's translational, and then rotational kinetic energy is 1/2, I omega squared. Well, if we have magnitudes here, right? So that's rotational kinetic energy. And remember what angular momentum is, right? It's I omega, right? Where this is a scalar and that's a vector. Right, so we have, well, we're not going to pay much attention to that, so let's just mark that out. Right? We have kinetic energy, rotational kinetic energy, and we have angular momentum. Right? So let's write down the expression for kinetic energy. Well, we'll move the 2 to the left-hand side, and we get our expression for kinetic energy in terms of the 3 components of angular velocity, omega x, omega y, and omega z. So if you remember, right, of course, we chose omega x, omega y, and we chose our z-axis to be the axis we're spinning about. Right? So here we go. There's if we're spinning about this this prolate object, omega naught, right? Then this is our z-axis, right? And initially, of course, all of our rotation is 0, 0, omega z, all in omega z. And so we're going to look at now what happens to that initial rotation vector as energy decreases, right? Kinetic energy decreases. Right. So these are the 3 components, right? We're not going to make any linearizations or anything in this case. Meanwhile, the angular momentum vector, right? If we square it, right, just to get the magnitude, then we have something similar to the kinetic energy case, except the i's are all squared here, right? I squared, ix squared, iy squared, and iz squared. Now we're going to do one other thing here, and we're going to consider the axisymmetric case, right? So that's ix. We're going to go back to the axisymmetric case. Why? Because the analysis becomes simpler. All the results we talk about here also apply to the non-axisymmetric case, but I can't derive them. Sorry. So we're going to consider the axisymmetric case just to make life easier. Right? So the analysis here applies to the axisymmetric case. The results apply to the non-axisymmetric case. So why do we use the axisymmetric case? Because it allows us to simplify are expressions for kinetic and angular momentum, kinetic energy and angular momentum, and put them in terms of each other, right? So specifically, if now we cross out, oops, that's not Z, that's X. Make that X. Re-highlight that. Make this X, right? Then we can pull the X component out of those two terms, and we have, right, this omega X plus omega Y squared term here, which of course, remember, is omega XY. Well, we'd rather not talk about omega XY because, well, it's just going to complicate life. So we're going to try and eliminate omega XY from these. We have two equations, right? Two equations, two unknowns. Well, really, this is going to be an unknown as well. So we'll try and eliminate omega XY from the system and get a single equation in terms of omega Z, right? Because that's really all we need. That's all we care about. So to do that, we're going to take the angular momentum equation and solve for omega Z, omega XY, right, in terms of angular momentum and omega Z. And we're going to plug that omega XY into the equation for kinetic energy, right? Because this is, of course, omega XY as well. So we're going to eliminate omega XY from the kinetic energy equation, right? So we do that, right? And, well, here's what happens, right? So we put omega XY over here. One of those IX's in the denominators gets canceled, but the other sticks around. And then we have an expression here, right, for kinetic energy in terms of angular momentum, which is fixed. That doesn't change. And omega Z, right? So this allows us, for fixed h, to express t in terms of the omega Z component of that angular velocity vector. So remember, here's our angular velocity vector. The omega Z component, right, is we've chosen to be, this is our Z direction, right, in the body fixed frame. And so then the component of that omega Z is this term here, right? So what happens to that over time? Is it going to, is omega Z going to increase? Well, probably not going to increase. Is it going to decrease? It can't increase, of course, because, right, initially, right, it's all in that Z component, right? So we're going to analyze what happens to that over time, right? So if it decreases, if omega Z decreases, it's got to go somewhere. So it's going to go over into the omega X and omega Y components over time. All right. So we have an expression here for now kinetic energy in terms of h, which is fixed, and omega Z here, which is not going to be fixed. So we're going to see what happens. Is it going to decrease or increase? So again, we eliminated omega XY, so we're not going to fuss with it, right? Everything we need to know, we can figure out in terms of omega Z. Now, I say that, but we're actually going to get rid of omega Z too, do a little, just to make the things slightly more geometric, right? So specifically, if you remember our body cones and our space cones, right here. So here's this is oblate object, there's our body cone, there's our space cone. And if you remember, we know that the angular momentum vector and the angular velocity vector are in the same plane as the z hat direction, right, which is that. So we know they're in the same plane. And we're going to look at how this z hat, the angle that this z hat vector makes with the angular momentum vector, which is, of course, fixed in space. Right. So is that that body, the orientation of the body, how is that going to evolve with respect to that fixed spatial vector? Right? And so we have actually, we have that original theta, which we defined earlier, which defines the orientation of that z component with respect to angular momentum. So we already defined what that was. And now we're going to play with it a little bit more. So we go back to that theta, and of course we use the definition of cosine here, right? Definition of cosine as the z component of angular momentum in the body fixed frame. So this is in body fixed frame, right? The angular momentum vector doesn't change in inertial space. It changes in the body fixed frame. So we define in the body fixed frame, right? So it's that z component in the body fixed frame divided by the total magnitude. Well, the z component, right, we have an expression for, right? It's Iz, which is inertia value, principal moment of inertia in the body frame, times the angular velocity component z, which we also in the body fixed frame. Okay. So what we're going to do is we're going to note that in our expression down here, remember this is our expression from the previous page, right? We're going to note that, oh, sorry, that's not the one from the previous page. This is the one from the previous page, right? It's got this term here, which we're going to try and eliminate, right? So here on this page, right, we've got I omega z, right? I z omega z equals h cosine theta. So we're just going to substitute that in, right? Right? And we do that, and that omega squared term becomes cosine theta squared term, and we get an extra h here on the top. So this is somewhat convenient because all the h's, we can pull them out. Right? Pull out all the h's. And so what we're going to do is we want to figure out how as t changes, as t goes up or t goes down, well, we're going to focus on the case where t goes down, what happens to theta? Does theta go up or down? Okay. And so to do that, we're going to take the derivative, right, in time. So we'll take the derivative in time, and well, this just becomes t dot. That's pretty easy. H is fixed, so it has no derivative. That dot term, constant term, disappears. This is constant, nothing happens. So we just need to take the derivative with respect to cosine theta, cosine squared theta. And this term is, of course, constant, so it doesn't change as well. So we just take the chain rule applied to cosine squared theta. The 2 comes down, right? We get cosine theta times the derivative of cosine, which is sine theta. It's just the chain rule. And then the chain rule again, out theta dot, right? So here we've got an expression now for t dot and theta dot in terms of each other. Right? So we simplify a little bit and bring our terms together. And what we're interested in is when t dot is less than 0, is theta dot less than 0 or theta dot greater than 0. So just to make life easier, we invert this a little bit, right? So we solve for theta dot, right, in terms of t dot. And now we want to look at the sign of this term. So remember, this term is going to be negative. And we want to figure out what's the sign of this term. And so obviously, well, this bit is positive. This bit is going to be positive, right, for all angles between 0 and pi over 2. So we're assuming that we're between 0 and 90 degrees. So that term is positive. It's going to be 0 at 0, so we're going to assume that theta is not exactly 0, but not exactly. Almost 0, but not. Between 0 and 90 degrees. So obviously, this analysis falls apart at theta precisely equal to 0, but nothing is precisely equal to 0. So anyway, we assume that's positive. And now the only thing that can change sign is this term right here, right? Iz and Ix. So remember, there are two main cases here, right? The spin where we've defined z, right, in that way, and the case where we've defined z that way. Or alternatively, and in the demonstration, we could have defined z that way. And in fact, actually, let's just do that. Let's just forget the prolate case entirely. Right. So there's two cases here, right? And so this is an axisymmetric case, so Ix equals Iy, so we don't have to fuss with that. And so the question is, right, is Iz greater than Ix? Well, in this case, right, we've defined it here, right, we have that z is the major axis. So Iz, in this case, is greater than Ix. Now, in this case, z is the, well, it's not an intermediate axis because it's not, there's no intermediate. I guess we can call it a minor axis, but it's minor / intermediate. Let's see. So in this case, in any case, Ix is, Iz is less than Ix, right? So, you know, the analysis doesn't really apply to this case because, right, we want Ix to equal to Iy, but so we'll ignore that bit right now. So in this case, Iz is technically equal to Iy, but again, our analysis doesn't really apply to that. In fact, actually, you know, just to be rigorous, I should, right, define this as our other case, right? In that case, Iz is clearly less than Ix, which is equal to Iy. Right? In any case, so let's consider these two cases. Let's call this case 1, and this is case 2. Now in case 1, the z-axis is a, oh, hold on, I've labeled them incorrectly, my bad. This is case 2, and this is case 1, right? So in case 1, we're spinning about the minor axis, z. So Iz is less than Ix. And so if Iz is less than Ix, well, this term is going to be less than or equal to 0, right? For case 1, right? And so as if t dot is less than or equal to 0, because this is negative, theta dot will be greater than or equal to 0. So t dot less than 0 in that case implies theta dot is greater than 0. So as energy decreases, the distance to the angular momentum vector will increase, right? So remember, in this case, our initial spin, right? In our initial spin, omega naught, the angular momentum vector is in this direction, right? So h, right? It's in that direction. So our initial theta is approximately 0. Right? So they're all lined up. However, as energy decreases, that angle will migrate. And actually, I'm drawing these on the wrong plot. Right? So in this case, well, we need that here too. Right. So initially, our angular momentum vector is lined up with the z-axis, and over time, right, that angle will increase, right, for some small perturbation of theta. Right? Theta dot greater than 0, so that the orientation of that z-axis will end up being at 90 degrees to the angular momentum vector. Right? And so finally, we'll have the angular momentum vector this way, which is the same in inertial space, and the z-axis, that long angle, will be over there. The other case, of course, here, we start with some, let's say, microscopic angle there, from the displacement of the angular momentum vector from the z-axis. And as energy dissipates, that angle decreases. So we'll rotate back. So actually, I probably should have drawn that a little bit better. So some initial omega h naught, that angle decrease back into alignment with the z-axis. Okay. So that's the case when the z is the major axis, right? And so this term is, in that case, great. That term right there is greater than or equal to 0 for case 2. Okay. And so, right, as t dot is negative, that implies that theta dot is negative, and so those disturbances from the initial orientation will damp out. So this is the orientation, the alignment of the angular momentum vector with the z-axis is stable in case 2, but unstable in case 2, in case 1. So when we talk about stability, we're talking about alignment of the body fixed z-axis and the angular momentum vector. And that's anywhere between, this is valid anywhere between 0 and 90 degrees. Not exactly equal at 0, though. We can also, use our Poinsot again if we like to illustrate these effects. And here this applies to the intermediate axis again. So here we've got lines of constant h squared over t. That's the lines on the Poinsot. And the angular momentum vector is fixed, or the angular momentum is fixed. And so as we vary t, as we decrease t, we're going to go from maximum kinetic energy to minimum kinetic energy. Right. So the maximum kinetic energy, for example, right, this line is T max, and this line is T min. And so as T decreases, right, we're going to evolve from this line to this line to this line to this line, which is the intermediate axis, right? So that's the kinetic energy of the intermediate axis, to this line, to this line, to this line, over to rotation about the major axis. And likewise, if we started in the intermediate axis, we'd be sort of floating along here, but we'd also migrate there, migrate there, and migrate there. And you don't see that on the YouTube videos. You don't see a migration to the major axis because there's no kinetic energy dissipation. Right? In the videos, we stay on a fixed line. Right? So Poinsot, have been around for a while. They were subject of a great deal of interest at some point. If you want to make one at home, there's actually a sort of homebrew way to do it. You can take the inertial ellipsoid. I don't know how you're going to construct that, but find a way. Hold at the center, and then just let it roll around an ink pad, and that gives you your lines of kinetic energy. That's sort of a clever hack, if you will, from Poinsot. It's a mathematical. You can prove mathematically that's how it works. It's just beyond the scope of this course, of course. Yeah. So the conclusion, right, is that we have this major axis rule, or minor axis theorem, if you like. So we still have that stability about spin about major axis is stable even with energy dissipation. But spin about any other axis is unstable, right? So we already knew that spin about the intermediate axis was unstable, but now we know that spin about the minor axis is unstable as well. So spin about the minor axis is unstable, but that's only the case if you have t dot, less than or equal to 0. Spin about the intermediate axis is unstable if t dot is less than 0 or t dot even is 0. Right? So either case. Right? So there's no case where major axis is unstable. one case, the minor axis there's only one case where the minor axis is unstable and the major axis is unstable. Intermediate axis is unstable no matter what. So the takeaway is that satellites should not be prolate objects. Right? That was our takeaway from this. I smell satellites, right? Should not be prolate. Which is unfortunate because rockets are prolate, and we launch satellites on rockets. So if you're going to put a satellite in orbit, then you've got a problem, right? So actually, we don't have spinning satellites too much, and this is sort of old tech. But basically, if you attach a rocket here, right, here's the rocket. There's the booster. So there are a lot of hacks to make these satellites not prolate. One of which is, of course, to discard booster. Discard your booster. Then it looks a little bit less prolate. The other one is, well, if you're going to spin your satellite, only spin part of it. And that's where we get these dual spin satellites. So spin that one for stability, but despin this part so that you're not, so the spinning part is oblate, but the overall object is prolate. So spin an oblate part of the spacecraft, but your overall spacecraft can be prolate. So the overall satellite is prolate, but the spinning part is oblate. Well, okay. So first of all, right, once you've done that, then you can just stabilize that spin by energy dissipation. So we can use these equations that we got for good as well as evil. So we have this fancy word nutation damper, which is just basically energy dissipation, right? So fuel sloshing is a passive form of nutation damper. Just dissipate energy. So nutation dampers, it sounds like a very fancy term, but in fact, actually, it's just energy dissipation. Right? Any way you want to do that, you just put like a spring in a can of oil, and that'll dissipate energy. Right? So that allows us to stabilize the spin axis. So that's how dual spin satellites work, right? You spin up the bottom part, and you don't spin up. You have a despun part, which is the top. Right? There's friction in the end, so sometimes, right, your top part spins a little bit, but that's how it is. And now I've got this this slide here, which I don't know, it's probably a little bit out of date, because of course it's not quite that simple, right? I mean, it's not that just the spinning part has to be oblate, right? So if your overall satellite is really prolate and your spinning part is oblate, it can still destabilize, but so there's some equations for that, basically, right? So we have to calculate these factors here, right? The relative moments of inertia of the intermediate axis divided by the spinning axis, the angular momentum of the spinning part of the spacecraft, spinning section. So we calculate that. Right, that goes over here. We use that to calculate this, which goes over there. There's a spin rate. And so we can make these plots, right, for different values of our parameter omega p naught here. So that goes there, that goes there, that goes there, that goes. So we make different plots for the geometry. And we can map out the how sort of oblate and prolate you're allowed to be using these charts here, right? So these shaded regions. So as you get here, right, as you see these relatively small areas, right? So change the size of the region. So this is the unstable region. And there, unstable region. And then we have stability regions in here. And so as these the relative angular momentum parts change, we hopefully would like to stay either in one of these two areas. This one is preferred, of course. Right. Those are the good regions. Right. Now they're slightly different. They're like statically unstable, but we can stabilize them fairly efficiently. So ideally, you want to be in the sort of bricky region here. So maybe we'll like eliminate them. So basically, the bigger these regions are, the better, right? So that's the best case, right? The second best case. And as this gets more negative, things get worse. Although this part gets, but anyway, so I don't want to talk about this in any great depth because, right, I guess it's all in the end a little bit out of date. But just the point is that the spinning part being oblate is not quite enough for stability of dual spin spacecraft. So. But we don't have many dual spin spacecraft anymore, so oh well. There's some more details. There's your energy. How much that's your nutation damper right there. So if you can stabilize this thing with nutation dampers, that's the question. So finally, that's that's the end of this section. Now I wanted to. I always like concluding these things with a video. Unfortunately, YouTube doesn't have many video. Well, it doesn't have any videos, and I can't find any online illustrating instability of the minor axis, the minor axis theorem, if you will. So I actually made my own. It's not great, but I'll show it to you anyway. So here it goes. And there we go. Oh, there's me. So obviously, that's not on my iPhone. It's just I had to create like some extra vertical space here, so I sort of rotated my camera vertically. So anyway, I'll unmute myself and let myself do the talking. Here we go. To illustrate so hopefully you can hear me. All right, class. So this is an illustration of the minor axis stability or instability theorem. So there are tons of demonstrations on the internet about the intermediate axis theorem, but apparently it's harder to illustrate the minor axis theorem. So I'm doing this on a what's actually an axisymmetric satellite. So in theory, this satellite should be stable about any of its axes because it's axisymmetric. And we can... Ha 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 ha. That's very funny. That's Siri. So Siri thought I was talking to her. It's got blue on the top, put little stars on the side. Hopefully that helps with contrast. And normally I would demonstrate this in class where there are higher ceilings, but due to home restrictions, I have to do it here. So hopefully you can see me. I think you can. So I'm going to throw it up. This is without damping, so there's no energy dissipation in this one. This is an empty box. Right? So you can use this with any sort of axisymmetric thing as long as you can introduce damping. Now I'm going to spin it up, and I'm going to spin it around its intermediate, its minor axis. Right? It has a major axis and two minor axes. It doesn't matter which one I choose, so it'll be a minor axis. So I flip it up. See, it looks pretty stable. Right? It spins. Very talented. Spins, no tumbling, no change of rotation axis at all. You can see the blue. Keep an eye on the blue. Spin it faster, spin it higher, I can miss it. Drop it on the floor, something like that. Straightforward. Now, let's introduce a bit of damping. So to introduce damping, it's a little bit tricky. It's not that hard. I got a bunch of Allen wrenches that were laying around the house. I'm going to sort of pad the the spacecraft so it doesn't produce too much noise. It doesn't make like loud bangs when it hits. And I'm going to fill my spacecraft with Allen wrenches. So this is the weirdest space mission you've ever heard of, but here it is. And then I'm going to put a little bit more damping on here so it doesn't make too much noise. And then I'll reattach the hood of the spacecraft. So, firmly in place. Now hopefully this one should have more damping. And so as the energy dissipates, it will move from spin about its minor axis to spin a slower spin about its major axis. We hope. We'll see how it works. So I'm going to flip it up like this. And when it comes down, hopefully, you should see it spinning around its major axis. So it'll be spinning sideways. The original spin, if I flip it up that, the spin axis is still here. The angular momentum vector is still here, right? But it's about an intermediate axis, and when it comes down, hopefully, it'll be spinning about this axis. So here we go. Let's give it a shot. Wobble there at the end. Sometimes it gets cleaner than others. But so there you have it. Energy dissipation causes a switch from spin about the major axis, or the minor axis, or one of the two minor axes here, to spin about the major axis at the end of the flight. That happened fairly quickly. All right, so that was very meta. Obviously, that was me not on Mars. Okay, so that concludes this lecture, and in fact, this is going to conclude the end of the lectures for this semester. There is one more lecture I sometimes give on detumbling, but I don't think I'll have, well, I know I won't have time to record that before the end of class. So I hope you enjoyed these lectures and maybe even watched them and learned something from them. Hopefully you will all absorb this knowledge and do well on the final exam. If you have any questions, contact me at office hours or offline. Thanks for watching.